Manila Bay, Philippines, February 1945. The water is dark, oil slicks shimmer under searchlights. The hulk of a knocked-out M4 Sherman sits half-submerged near the dock, its turret blown off, its hull torn open by internal ammunition explosion. Japanese Army Captain Hiroshi Tanaka wades through knee-deep water toward it. Behind him, 2 enlisted men carry tools and measuring equipment. Above them, American artillery pounds Japanese positions in the city. The sounds echo across the bay. Tanaka has 48 hours before his unit withdraws further inland. 48 hours to examine this tank, document what he finds, and report to division headquarters. He is a metallurgical engineer in civilian life, drafted into service in 1943, assigned to the Army Technical Research Institute. This is his 3rd captured American tank inspection. Each time, he sees the same things that should not be possible. Things that contradict everything he learned about. Mass production. He climbs onto the hull. The metal is still warm from the fire that consumed the crew. He ignores this, ignores the smell, focuses on the seams, runs his hand along the welded joint where the sponson meets the lower hull. The weld is continuous, uniform, no gaps, no slag, no porosity visible even in the torn sections where the metal has been peeled back by the explosion. He signals to the enlisted men. They hand him a portable grinding tool. He grinds away a small section of weld to examine the cross-section. The penetration is complete. The weld metal has fused entirely through the base metal. Root penetration is 100%. This should not be possible in production welding, not at the speeds necessary to build tens of thousands of tanks. Complete penetration requires precise control of arc voltage, travel speed, electrode angle. It requires skill, time, attention. Yet here it is, on a mass-produced vehicle, on every seam he examines. Tanaka measures the weld dimensions, records them in his notebook, takes photographs with a Leica camera, documents everything. That night, by candlelight in a ruined warehouse, he writes his report. Subject tank, M4A3 Sherman, serial number partially visible, manufactured approximately mid-1944, based on features observed. Hull construction, entirely welded, no rivets observed in primary structure. Weld quality, exceptional for mass production. All major seams examined show complete penetration, minimal defects, uniform appearance suggesting automated or semi-automated process. Material, rolled homogeneous armor, approximately 64 mm frontal thickness, 38 mm side. Welding method unknown but clearly superior to Japanese capabilities. Recommendation: immediate study of American welding techniques. Current Japanese methods inadequate for modern armored vehicle production. The report travels up the chain of command. It reaches Tokyo 3 weeks later. Then, Manila has fallen. Captain Tanaka is dead, killed by American tank fire during the retreat. His report is filed with dozens of similar assessments, all saying the same thing. American welding is beyond Japanese capacity to replicate. The Americans have not just outproduced Japan, they have done so with methods Japan does not possess and cannot acquire. Not now, not while the war continues, perhaps not ever. This is the story of that welding, not the dramatic story of tank battles or heroic last stands, but the quiet story of how industrial capacity, manufacturing philosophy, and production technology determined the outcome of the Pacific War before a single shot was fired. It is a story about seams and joints, about electrodes and arc voltage, about the difference between making things by hand and making them by machine, about craft versus industry, quality versus quantity, the perfect versus the good enough. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. When people discuss technological advantages in World War II, they focus on the obvious innovations. Radar, the atomic bomb, jet engines, aircraft carriers. These technologies were revolutionary. They changed warfare fundamentally. But there were other advantages. Quieter advantages. Advantages that lived not in laboratories, but in factories. not in the inventions themselves, but in the ability to produce inventions at scale. Welding was one of these advantages. By 1944, the United States had perfected industrial welding to a degree unmatched by any other nation. American factories could join steel armor plates faster, more consistently, and with higher quality than competitors. This capability was not secret. It was not classified. Japanese engineers could examine captured tanks and see exactly how American welding worked. They could measure the welds, photograph them, analyze the metallurgy. They could understand completely what the Americans were doing. Understanding and replicating are different things. A concert pianist can hear a Chopin nocturne and understand every note. That does not mean they can play it. Technical knowledge is not the same as technical capacity. Japan understood American welding, but Japan could not match it, not with the industrial base they possessed, not with the resources available, not within the constraints of wartime production. The gap was unbridgeable. To understand why requires going back decades before the war, back to when welding itself was new, back to when joining metal meant heating it in a forge and hammering it together, back to the origins of industrial metalworking. Metal joining is as old as metallurgy itself. Ancient blacksmiths discovered that iron, heated until nearly molten, could be hammered together to create a single piece. This forge welding required enormous heat, tremendous skill, and exhausting physical labor. A master blacksmith might spend days creating a single sword blade, folding and welding the steel repeatedly to create the desired properties. For thousands of years, this was the only way to join metals. Forge welding built medieval armor, Renaissance cannons, the tools and weapons of entire civilizations, but it was fundamentally a craft, not an industry. It relied on individual skill. It could not scale. A master blacksmith could train apprentices, but training took years. Production was limited by the number of skilled craftsmen available. This was adequate for pre-industrial societies. It was completely inadequate for the 20th century. The breakthrough came in the late 1800s. Electricity, that transformative technology of the industrial age, provided the key. In 1881, French engineer Auguste de Méritance discovered that an electric arc between carbon electrodes could generate sufficient heat to melt steel. This was revolutionary. Instead of heating metal in a forge, electricity could melt it directly at the joint. The process was faster, more controlled, and did not require massive forges or endless hammering. But early arc welding was crude. The equipment was unreliable. The process was poorly understood. Welds were inconsistent, often weaker than the base metal. Contamination from atmospheric oxygen and nitrogen created brittle welds prone to cracking. Through the 1890s and early 1900s, researchers and inventors gradually solved these problems. Coated electrodes were developed that provided both filler metal and protective flux. Shielding gases were introduced to protect the weld pool from contamination. Automatic electrode feeders eliminated the need for constant manual manipulation. By 1920, welding had matured enough for industrial use. Ships were being welded instead of riveted. Pipelines were welded. Building construction employed welding. But the technology was still evolving. The real breakthrough came with submerged arc welding, developed in the early 1930s. This process buried the welding arc beneath a layer of granular flux, providing complete protection from the atmosphere while dramatically increasing the deposition rate. A welder using submerged arc welding could lay down weld metal 5 to 10 times faster than manual methods. This was the technology that would build the Sherman tank, but technology alone was not enough. Industrial implementation required investment in equipment, training of workers, development of quality control procedures, and integration into production systems. This took time. It took capital. It took a culture of industrial innovation. The United States had all of these. Japan had some of them. The difference mattered. If this deep dive into history is worth your time, hit that like button and let us know in the comments what historical topic you'd like us to cover next. American industry in the 1930s was the most advanced in the world. The automobile had created an entire ecosystem of supporting industries: steel mills, parts manufacturers, tool and die shops. The assembly line, perfected by Henry Ford in the 1910s, had become the standard for mass production. By the 1930s, American factories were producing millions of automobiles annually. Each car contained hundreds of welded joints. The industry had developed specialized spot welding equipment, automated welding lines, and quality control systems. When war came, this infrastructure could be repurposed almost immediately. The same factories building car bodies could build tank hulls. The same workers welding automobile frames could weld armor plate. The same engineers designing production systems for civilian vehicles could design them for military equipment. The transition was not seamless, but it was faster than anyone expected. By early 1942, less than 3 months after Pearl Harbor, American factories were already producing Sherman tanks. The Sherman's design reflected American manufacturing philosophy. The tank was not designed to be the best. It was designed to be good enough and producible. The hull was constructed from rolled armor plates welded together. This was simpler than the cast hull of the M4A1 variant and faster than riveted construction. The plates were cut from sheet steel, using industrial cutting equipment. They were formed using huge presses. They were assembled in fixtures that held them precisely in position, while welders joined them. The welding itself employed multiple processes depending on the joint. For critical structural welds, skilled operators used shielded metal arc welding with coated electrodes. They worked methodically, laying down weld beads in careful sequence to minimize distortion and ensure full penetration. For long, straight seams, automated submerged arc welding was employed. The equipment moved along the joint at constant speed, laying down uniform welds far faster than any human could achieve manually. Quality control was integrated into the production process. Inspectors examined every weld visually. They used penetrant dye to detect surface cracks. They employed magnetic particle inspection to find subsurface flaws. Critical welds were X-rayed. The rejection rate was surprisingly low, typically under 5%, because the processes were well controlled. When defects were found, they were ground out and re-welded. No defective tank left the factory. The electrodes used for armor steel were specially formulated. They contained high levels of nickel, which provided toughness and crack resistance. The formulation had been developed through extensive research by electrode manufacturers working with the military. The rods were manufactured to tight specifications. Each batch was tested before use. This attention to detail ensured that welds met minimum strength requirements consistently, across thousands of tanks. Training was systematic. The American Welding Society had developed standardized curricula and certification programs during the 1920s and 30s. When war production began, these programs expanded dramatically. Vocational schools offered accelerated courses. The government funded training centers specifically for defense workers. A person with no previous experience could learn basic welding in 6 to 12 weeks. This was possible because the work was being systematized. Automated equipment required operators, not craftsmen. Semi-skilled workers could produce good results if properly trained and supervised. Women entered the welding workforce in unprecedented numbers. When men left for military service, women filled the positions. By 1944, women comprised 30 to 40% of welding personnel in many defense plants. They operated equipment, performed inspections, and often matched or exceeded male productivity. The iconic Rosie the Riveter image is misleading. Many of these women were welders, not riveters. The war proved that welding did not require masculine strength. It required training, attention to detail, and consistency. The scale of Sherman production was staggering. In 1942, American factories produced approximately 10,700 Shermans. In 1943, production peaked at 21,100 tanks. In 1944, 17,300 were built. Even in 1945, as the war wound down, production continued at thousands per month. The final total reached 49,324 tanks of all variants. Each tank required approximately 60 to 80 major weld seams, depending on variant and configuration. Each seam might be several feet long. The total length of welding per tank was measured in hundreds of feet. Multiply this by 49,000 tanks. The result is tens of millions of feet of weld, millions of pounds of electrode consumed, millions of hours of arc time. Every single foot of weld had to meet quality standards, had to be strong enough for combat, had to hold under stress, impact, and vibration. The consistency required to achieve this is almost incomprehensible. It represents not just industrial capacity, but industrial discipline. 49,000 tanks, each built to specification, each with welds that met standards, each delivered to the military, ready for combat. This was the arsenal of democracy in action, not producing perfect tanks, producing adequate tanks in overwhelming numbers. Japan approached tank production from entirely different circumstances. Japanese industry in the 1930s was capable but constrained. The nation had modernized rapidly since the Meiji Restoration of 1868. In just 70 years, Japan had transformed from a feudal society to an industrial power. But that industrialization was uneven, concentrated in certain sectors, limited by resource scarcity. Japanese shipbuilding was world-class. The Imperial Japanese Navy operated some of the most advanced warships afloat. The battleship Yamato, completed in December 1941, displaced 72,000 tons fully loaded. Its 9 18-inch guns were the largest ever fitted to a warship. Its armor was the thickest. Its construction quality was superb. Every rivet, every weld, every plate was crafted with meticulous attention to detail. Yamato represented Japanese industrial capacity at its finest. But Yamato also represented Japanese industrial philosophy. The ship took nearly 4 years to build. It consumed enormous resources. It required Japan's best craftsmen, finest materials, most advanced equipment. It was a masterpiece. But it was not mass-producible. Japan built only 2 Yamato-class battleships. The United States, during the same period, built 24 Essex-class aircraft carriers. Quality versus quantity, craft versus industry. The philosophies could not have been more different. Steel allocation reflected these priorities. In 1941, approximately 60 to 65% of Japanese steel production went to the Navy. The Army received what remained. This was not arbitrary. Japan was an island nation dependent on sea lanes. The Navy was considered essential for national survival. The Army, fighting primarily in China where opposition was poorly equipped, received lower priority. This made strategic sense until the war expanded to face America and Britain. Tank production suffered from these constraints. The Imperial Japanese Army recognized the need for modern armored vehicles. Japanese tanks had performed adequately in China during the 1930s, but Chinese opposition was weak, equipped primarily with imported light tanks and inadequate anti-tank weapons. When Japan faced Soviet armor at Khalkhin Gol in 1939, Japanese tanks proved inferior. The Type 97 Keiha, Japan's main medium tank, was outmatched by Soviet BT-5 and BT-7 light tanks and devastated by 26 medium tanks. The lesson was clear. Japanese armor needed improvement, but resources were not available for major upgrades. The Keiha continued in production, largely unchanged. Its hull was entirely riveted. Rolled armor plates were cut, drilled, and joined with steel rivets. This was traditional construction, familiar to Japanese manufacturers. Riveting required relatively simple equipment, a drill press, a rivet gun, skilled workers. The process was straightforward. Results were easy to inspect visually, but riveted construction had significant disadvantages. Riveted joints were weaker than welded joints of equivalent weight. Under impact, rivets could shear or pop loose. The rivet heads created stress concentrations where cracks could initiate. Most critically for combat, when armor was struck by anti-tank fire, the impact could cause interior rivet heads to detach and become projectiles, injuring or killing crew members, even when the armor was not penetrated. This phenomenon, called spalling, was a known problem with riveted armor. British tanks in World War I had suffered from spalling. By World War II, Most modern designs used welded construction to avoid this issue, but Japan, constrained by capacity and resources, continued with riveted construction. Some welding was employed. The Type 1 Chi-He, introduced in 1943, featured a welded frontal glacis plate. This single improvement significantly enhanced protection, but the rest of the hull remained riveted. Production was limited to 170 units. All were reserved for home defense. None saw combat. Why so few? The answer lies in Japanese industrial constraints. Welding equipment was scarce. Automated welding systems were virtually non-existent outside of shipyards. Most welding had to be performed manually by skilled workers. Training took time. A skilled welder required months or years of experience. During wartime, such workers were desperately needed in shipyards building and repairing warships. Diverting them to tank production was not feasible. Even when welders were available, the work was slow. Manual welding of armor plate, with its high carbon content and thick cross-sections, required careful preheating to prevent cracking. Each pass had to be made at controlled travel speed with proper electrode angle. Cool down had to be gradual to avoid introducing residual stresses. A skilled welder might spend an entire day completing the welds for a single tank hull. By contrast, American automated systems could complete the same work in hours. The disparity extended beyond welding to overall production philosophy. Japanese tank manufacturing was more akin to craftsmanship than mass production. Each tank received individual attention. Quality control was rigorous, but it relied on inspection rather than process control. Skilled workers took pride in their work, spending extra time to ensure perfection. This resulted in excellent individual tanks, but it could not produce them in the numbers needed. Japan manufactured approximately 6,700 tanks of all types during the entire war. This includes light tanks, medium tanks, and tank destroyers. The majority were Type 97 Chihas and Type 95 Hago light tanks. Production peaked in 1942 at approximately 1,200 tanks, declining thereafter as resources became scarcer. The average across the war was approximately 140 tanks per month for the entire nation. Compare this to American Sherman production. In peak months of 1943, American factories produced nearly 2,000 Shermans alone, not counting light tanks or other armored vehicles. The ratio is approximately 14:1. For every tank Japan produced, America produced 14 Shermans. This disparity was not due to lack of effort or competence. It was structural, systemic, the result of fundamentally different industrial capabilities. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The steel shortage was critical. Japan's steel production in 1941 was approximately 6.8 million metric tons. America's was 75.5 million metric tons. The ratio is approximately 11:1. Japan could not build more tanks because it lacked steel. It could not produce more steel because it lacked iron ore and metallurgical coal, both of which had to be imported. Before the war, Japan imported iron ore primarily from Malaya and the Philippines, coal from Manchuria and China. When war began, these supply lines became vulnerable. American submarines began interdicting Japanese shipping in early 1942. By 1943, submarine warfare had become devastatingly effective. Japanese merchant shipping losses mounted catastrophically. Ore carriers were priority targets. By 1944, Japan's steel production had declined significantly due to lack of raw materials. By 1945, it had nearly collapsed. Tank production followed the same trajectory. But even with adequate steel, Japan could not have matched American welding capacity. The infrastructure did not exist. American factories had decades of experience with industrial welding. They had developed specialized equipment. They had trained workforces. They had integrated welding into production systems designed for mass output. Japan had welding capability in shipyards, but shipyards were building warships, not tanks. The equipment, the workers, the expertise were not transferable on short notice. Japanese engineers were well aware of American welding techniques. Technical intelligence gathered from captured equipment provided detailed information. Reports from the front described American construction methods. Japanese metallurgists analyzed weld samples. They understood what the Americans were doing. They could specify exactly what equipment and processes were needed to replicate it. But knowledge without capacity is useless. Consider Captain Tanaka's report from Manila. He documented American welding in precise detail. He recommended immediate investment in automated welding equipment. He suggested reallocating resources from naval to army production. He argued that without matching American manufacturing methods, Japan could not compete. The report was correct in every particular, and completely impossible to implement. By February 1945, when Tanaka wrote his report, Japan's situation was desperate. The Philippines were being lost. Okinawa would be invaded within weeks. The home islands faced imminent attack. Strategic bombing had begun destroying Japanese industrial capacity. Even if Japan had possessed the resources to build welding infrastructure, there was no time. The war would be over within months. Tanaka's recommendations, like dozens of similar reports from other engineers and officers, were filed and forgotten. The tank battles in the Pacific told the story more clearly than any report. At Tarawa in November 1943, American Shermans encountered Japanese Type 95 Hago light tanks. The Hago weighed 7.5 tons, mounted a 37mm gun, and had riveted armor 16mm thick maximum. Sherman's 75mm gun could penetrate it at any range from any angle. The Hago could not penetrate the Sherman under any circumstances. The engagement was one-sided. At Saipan in June 1944, Japanese armor launched a night counterattack with approximately 31 tanks, including Chihas and Hagos. They attacked American Marine positions supported by Sherman tanks, bazookas, and anti-tank guns. By dawn, all 31 Japanese tanks had been destroyed. American armor losses were 0. The battle demonstrated the futility of Japanese armor against American equipment. At Iwo Jima in February 1945, Japanese defenders had no operational tanks, having learned that armor could not survive against American firepower. At Okinawa in April 1945, a handful of Japanese tanks fought from concealed positions, achieving occasional successes through ambush but unable to affect the battle's outcome. The pattern was consistent across every engagement. Japanese armor was outmatched, outnumbered, and ultimately irrelevant to the war's outcome. The welding that held Sherman hulls together was part of this story. Not the dramatic part, not the part that makes exciting battlefield narratives, but the foundational part, the part that made everything else possible. Without those welds, there would be no Sherman tanks. Without Sherman tanks, the island-hopping campaign would have been far more difficult, far costlier, perhaps impossible. American Marines could land on beaches knowing they had armor support, knowing their tanks could defeat anything the Japanese possessed. This confidence affected tactics, morale, and outcomes. Japanese defenders knew the opposite. They knew American tanks would come. They knew their own armor was inadequate. This knowledge shaped defensive strategies. Dig in, create concealed positions, fight from caves and bunkers where tanks cannot easily engage, rely on anti-tank guns and close assault tactics. These were defensive measures born of weakness, not offensive options born of strength. The psychological dimension of material superiority should not be underestimated. The welders who built Sherman tanks never saw combat. Most never saw a completed tank in action. They worked in factories in Detroit, Chicago, Pittsburgh. They performed their work, collected their wages, went home. They did not consider themselves heroes. They were doing a job. But their work mattered. Every weld they made, every seam they joined, contributed to a tank that would carry 5 men into battle. Some of those men would survive because the tank protected them, because the armor held together, because the welds did not fail. Japanese workers building Chihas worked just as hard, with just as much dedication. They took pride in their craftsmanship. They built tanks to the best of their ability, with the resources available, but they were working within a system that could not compete. not because they were less skilled, not because they worked less hard, but because the system itself, the industrial infrastructure, the resource base, the manufacturing philosophy, was inadequate for modern industrial warfare. This is the tragedy of the Pacific War from the Japanese perspective. Individual excellence could not overcome systemic disadvantage. Japanese soldiers were brave, often fanatically so. Japanese officers were skilled and determined. Japanese workers were dedicated and competent. None of it mattered. When one side can outproduce the other by an order of magnitude, when one side has resources the other lacks, when one side has industrial capacity the other cannot match, the outcome is determined before fighting begins. The welding was simply one manifestation of this disparity, but it was a telling one. It represented the difference between craft and industry, between making things by hand and making them by machine, between seeking perfection and accepting adequacy, between quality and quantity. American chose quantity. American chose industrial methods. American chose good enough. And America won. Post-war development validated this approach. The Sherman remained in service long after the war ended. The U.S. Army used Shermans through the Korean War in the early 1950s. Allied nations received thousands through military aid programs. Israel used upgraded Shermans through the 1960s and into the 1970s. Some Sherman variants remained in service with South American militaries into the 1980s. These tanks, built with 1940s welding technology, proved remarkably durable. Welded hulls remained structurally sound through decades of use. Welds that had been made in American factories during the war held together through thousands of miles of operation, through combat, through hard use in peacetime training. This longevity validated the American approach. Industrial welding, properly executed, was sufficient for a tank's entire service life. Artisanal perfection was unnecessary. Japan's post-war tank development followed a different path. During occupation, Japan was prohibited from manufacturing military equipment. When the prohibition was lifted in the 1950s, the newly formed Japanese self-defense forces initially used American M4 Shermans provided through military aid. Japanese crews trained on the same tanks they had once fought against. They studied the construction, the welding, the design philosophy. They learned the lessons America had applied during the war. When Japan developed its first post-war tank, the Type 61, completed in 1961, it incorporated those lessons: welded hull construction, standardized components, design for mass production. The artisanal approach was abandoned. Subsequent designs, the Type 74 in the 1970s and Type 90 in the 1990s, continued this evolution. Modern Japanese tanks employ robotic welding, automated inspection, and advanced manufacturing techniques. Japan became a leader in welding technology, but that expertise came too late for the war generation. The men who fought in Chihas and Hargos, who faced Shermans with inadequate equipment, who died in tanks that could not protect them, never saw Japan's industrial transformation. They paid the price for decisions made decades before. The war began. Decisions about industrial investment, about resource allocation, about manufacturing philosophy. Decisions that determined outcomes before the first shot was fired. Captain Tanaka, examining that captured Sherman in Manila Bay, understood this. His report was not just technical documentation. It was an acknowledgement of defeat. Not defeat in that particular battle. Defeat in the industrial competition that determined the war's outcome. He could measure the welds. He could analyze the metallurgy. He could specify exactly what Japan needed to match American capabilities. But he could not create the industrial base to implement it. No one could. Not in time. Not with the resources available. Not while the war consumed everything. The welding technology that built the Sherman represents something larger than technical achievement. It represents a way of thinking about production, about war, about how industrial societies mobilize resources. The Americans did not seek to build the perfect tank. They sought to build adequate tanks in overwhelming numbers. This pragmatism, this willingness to accept good enough, this focus on quantity over quality, was itself a kind of innovation. It required letting go of perfectionism, accepting that 80% solutions produced fast enough would defeat 100% solutions produced slowly. Japan never made that transition. Japanese culture valued excellence, craftsmanship. The spirit that created samurai swords folded 10,000 times. That spirit built Yamato, the greatest battleship ever constructed. But that spirit could not build 49,000 tanks. It could not mass-produce adequate equipment fast enough to compete with American industry. Cultural values that served Japan well in peacetime became liabilities in the industrial war. This is not to criticize Japanese culture. Cultural values are neither good nor bad in the abstract. They are suited or unsuited to particular circumstances. Japanese craftsmanship built beautiful things, durable things, excellent things. But modern warfare did not reward excellence. It rewarded adequacy at scale. It rewarded the ability to produce thousands of mediocre weapons faster than competitors could produce hundreds of excellent weapons. This was the mathematics of industrial war. Brutal, unforgiving, inarguable. The legacy of Sherman welding extends into the present. Every modern armored vehicle uses welding extensively. The M1 Abrams, America's current main battle tank, has a welded hull made from composite armor incorporating depleted uranium. Advanced robotic welding systems join components with precision impossible for human welders. Laser welding creates seams without filler metal. Friction stir welding joins aluminum armor without melting it. The technology has advanced dramatically, but the principles remain the same. Join materials by fusing them together. Control the process to ensure quality. Do it efficiently enough to make production economically viable. Do it consistently across thousands of vehicles. These principles, applied in American factories during World War II, continue to define military manufacturing today. The scale has changed, the technology has advanced, but the fundamental approach, industrial rather than artisanal, quantity over perfection, remains unchanged. Thank you for reading. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.